Hello everyone and welcome to General Chemistry 2, lecture number 16. This is the third acids and bases lecture. This one is on buffers. This covers OpenStax section 14.6. We're going to start by discussing the common ion effect. So we're going to pose a scenario. We've got a mixture of acetic acid, which we've learned is a weak acid, and sodium acetate. This is a salt that contains acetate, which is the conjugate base of acetic acid. These two things are being mixed together in an aqueous solution. Question being posed here is, how do all these ions being in the same solution affect one another? The hint here is that this is related to Le Chatelier's principle. So here, number one, we can see the acid dissociation reaction for acetic acid. This is acetic acid dissociating into a hydrogen ion and acetate. We know that if this was in water, you would form H3O+, but I'm just showing the simplified version here without water. Then this second chemical reaction here is showing the dissociation of sodium acetate, which is an ionic compound. It's a strong electrolyte due to sodium's solubility, and so this will fully dissociate into sodium ions and acetate ions. So let's look at how these ions being in the same solution are going to affect one another and how this relates to Le Chatelier's principle. So let's look at a common ion ice problem. What is the pH of a solution containing 1 molar acetic acid and 1 molar sodium acetate? The acid dissociation constant, or Ka, of acetic acid is 1.8 times 10 to the negative fifth. Alright, so we are looking for a pH here. So we're going to start by writing out our acid dissociation reaction. So this is the dissociation reaction for acetic acid. Again, I'm just showing the simplified version without water here. So we have acetic acid, and I'm using the equation editor, so this is how the double arrows look in the equation editor. So this is meant to be the equilibrium arrow, forward and reverse, forming the H plus and the C2H3O2 minus. Next, we can set up our ice table. So we're calling I initial, C change, and E equilibrium. Our initial concentration of acetic acid is 1 molar. Our initial concentration of H plus is 0 molar, and the initial concentration of acetate is also 1 molar, coming from the 1 molar sodium acetate. We're still going to be moving in the forward direction, given that we have 0 H plus ions, so minus X for the acetic acid and plus X for both of the products, giving us equilibrium concentrations of 1 minus X, X, and 1 plus X for acetic acid, H plus, and acetate, respectively. Now we can set up our Ka expression. So Ka equals the concentration of H plus times the concentration of C2H3O2 minus the acetate, divided by the concentration of the acetic acid. Then we can take these equilibrium values and plug them in. So X for H plus, 1 plus X for acetate, and 1 minus X for the acetic acid. This is all equal to the value of Ka, which was given in the problem, as 1.8 times 10 to the negative fifth. I'm skipping some algebra steps here to save time. If you are unsure about how to get from the setup here to this final answer, please review one of my earlier lecture videos on the ICE method. But essentially what you would do is you would take this on the bottom, you would move it over to the right side, then you also need to distribute this X, and then you're going to end up combining like terms. This is going to leave you a quadratic polynomial, which requires the use of the quadratic equation or solver on your calculator if you are using like a TI-36X that has the solver function. And you should find that X is equal to around 1.799 or so times 10 to the negative fifth. Now we can find the pH. So remember that the pH is equal to the negative log of H plus. And here, the equilibrium concentration of H plus is just X, so the pH is the negative log of X. When you plug this value in, you should get a pH of around 4.745. All right. Now, I do also want to note that this X value is much smaller than the initial concentration. Could we have used a shortcut here? The answer is yes. In a lot of these weak acid, and we'll see later, weak base titrations, shortcut, that small x approximation that we learned about towards the end of our ice method lecture is often going to be viable. So notice here, you could cross out both the minus x and the plus x, and you get an x value of around 1.8 times 10 to the negative fifth, which is almost identical to the value that we got using solver and working through the quadratic equation. All right, now let's look at a problem. Let's look at the same problem, but let's ask ourselves, what would the pH be if we didn't start with 1 molar of the conjugate base? So we're going to remove the 1 molar of the sodium acetate. We'll again write out our dissociation reaction, plug in our initial concentrations of 1 molar for the acetic acid and 0 for both products. Still, our changes would be minus x and then plus x plus x. Equilibrium concentrations of 1 minus x, and then x for both of the products. We can set up our Ka expression. So this is still H plus times acetate over acetic acid. X gets plugged in for both the H plus and the acetate. 1 minus x plugged in for the acetic acid. We can again use solver here. The small x approximation would reasonably work well on this problem, but here I'm showing you the answer I got by working through the algebra, and I came up with x equals 4.234 times 10 to the negative third. So now when we plug this into our pH expression, again remembering that pH equals the negative log of H plus, which is just x once again. So we can take this value, plug it in, and we get a pH of 2.373. Note that this pH is very different than the one we got on the previous problem when we did start with that 1 molar of the weak base. Why is this? Think about this in context maybe of Le Chatelier's principle, right? So Le Chatelier's principle tells you which direction the reaction is going to proceed to establish equilibrium. Here we've got a lot of reactant and no product, so the reaction is going to shift pretty far to the right, which results in a fairly large amount of H plus being produced, and we get a low pH because it's more acidic, more H plus. Whereas if we start with 1 molar of acetate, we've already got some product here, so the reaction is not going to shift right as far. Not as much H plus is produced, and so the solution is less acidic and then has a higher pH. And so this solution, the solution we showed in the first problem, is a buffer. A buffer solution or buffered system is made of a weak acid-base conjugate pair. So you must have a weak acid or a weak base and a salt that contains its conjugate base or conjugate acid, depending upon if you've got a weak acid, you'd want the conjugate base. If you have a weak base, you would want the conjugate acid. So a few examples of buffer solutions. The one we just looked at, acetic acid and sodium acetate. This is a buffer solution. Hydrofluoric acid and potassium fluoride. Remembering that hydrofluoric acid is a weak acid, then potassium fluoride would present or provide us with the conjugate base. Ammonia and ammonium chloride. Ammonia is a weak base, and then ammonium chloride would give us the conjugate acid. These are not buffer solutions. This one, strong acid, strong base, not a buffer. This one has a weak base and a strong base, definitely not a buffer. Here we've got a weak acid and a strong acid, also not a buffer. So it must be a weak acid with its conjugate base or a weak base with its conjugate acid. Important to note here that a buffer solution has the ability to resist changes in pH upon the addition of small amounts of an acid or base. This is part of the reason why we saw that first example problem, the pH was a little bit higher than the second, because it had both acid and base present in solution, and so because of this, it can resist changes in pH. So let's examine how a buffer works. Let's consider a buffer that contains aqueous acetic acid with sodium acetate. If we were to add a bit of strong acid like HCl, hydrochloric acid, to this buffer, that HCl that's being added, or more specifically, the H plus that's being added, is going to be neutralized by the acetate ion, a weak base, and this will produce a little bit more acetic acid, a weak acid. Because weak acids do not produce nearly as much as hydronium ions as strong acids do, the pH will not change much, if it even changes at all. So here we're showing the chemical reaction. where we add a strong acid to the buffer. So that strong acid reacts with the weak base from the buffer, producing some weak acid along with, technically this is the conjugate base, but as we learned, Cl- since it's the conjugate base of a strong acid, it does not act as a base. If the same amount of HCl is added to just water, all of it would be converted into H3O+, since it's a strong acid, and as the concentration of hydronium ions increases, the pH would change significantly. So this is what's so useful about buffers. Add a little bit of strong acid to it. That strong acid will react with the weak base present in the buffer, and this helps resist pH change. Similarly, we could add a bit of strong base, like sodium hydroxide, to this buffer. This will be neutralized by the acetic acid, which is a weak acid, which will produce more sodium acetate, a weak base. And once again, because weak bases do not produce nearly as much as hydroxide ions as strong bases do, the pH will not change much, if at all. And here we can see that reaction. We have the weak acid from the buffer, acetic acid, plus the strong base, the sodium hydroxide, being added. The H from the weak acid reacts with the OH from the strong base to form water. This leaves behind sodium and acetate. And so this is the formation of a little more of that sodium acetate, which is a weak base. But again, that weak base is a lot weaker than this strong base is, so the pH won't change much. If we were to add the same amount of NaOH to just water, there's nothing to neutralize those added OH ions. That base just dissociates, and we get a rapid increase of hydroxide ion concentration, which is going to result in a significant and rapid pH change. All right, let's look at some visual examples of buffers. So here's the before picture. So here, letter A, we've got an unbuffered solution on the left, and then we've got a buffered solution on the right. They both have the same pH of 8.0. They are basic, and they have this yellow color because they're using an indicator methyl orange, which has a yellow color at this pH. And then here, letter B, we're showing what occurs after the addition of 1 milliliter of 0.01 molar hydrochloric acid. The buffered solution has not detectably changed its pH. Notice that its color didn't change at all. Whatever this buffer was, the weak base that was present neutralized the added acid. pH didn't change, color didn't change. The unbuffered solution, its pH changed rapidly, and we notice then the change in color. Methyl orange appears red with an acidic pH. So now the solution has a pH of around 4. Even just 1 milliliter of this 0.01 molar hydrochloric acid was enough to rapidly change the solution from basic to acidic because it's unbuffered. A real-life example of a buffer is your blood. So your blood uses a bicarbonate buffer system. Dissolved carbon dioxide produced during cellular respiration travels through the bloodstream to be exhaled by the lungs. This dissolved CO2 will react with H2O in your blood, forming carbonic acid, H2CO3. This carbonic acid can further dissociate to form the bicarbonate ion, HCO3-. And this is our buffer system. The bicarbonate, the HCO3-, is a weak base, and it is capable of neutralizing acids. Your body produces acids through various metabolic processes, like lactic acid and fatty acids. Then the carbonic acid, this is a weak acid. It will neutralize bases. So your body also produces some basic substances as a result of its metabolic processes, such as urea and creatine. Imbalance or disruption of the equilibrium in this buffer system can lead to acidosis if your pH is too low, or alkalosis if your blood pH is too high. One thing I also want to briefly describe here is what happens when you begin to hyperventilate. So you've probably seen this maybe like in a show or a movie before where someone's hyperventilating and they have them breathe into a brown paper bag. There is an actual reason for this. So when you're hyperventilating, you're exhaling too much carbon dioxide from your lungs. So if you think about this equilibrium here, if you exhale too much from your lungs, you're basically removing a reactant. And if we think about the context of Le Chatelier's principle, you remove a reactant, the equilibrium shifts left. And so as it shifts left, this removes acid from your blood. This raises the pH of your blood, making it more basic. which leads to a condition known as respiratory alkalosis. Respiratory alkalosis can be prevented by having the person breathe into a paper bag. If you breathe into a brown paper bag, this results in you inhaling some of that exhaled CO2, and so this will help to re-establish or rebalance this equilibrium and can stabilize your blood pH. All right, let's have you practice identifying some buffer systems. Which of the following are buffer systems? So from these four, decide which of them are buffer systems. Please go ahead and pause the video and then decide which are buffers. Oh, sorry about that. I thought the answers here, or I thought I had the answers on the next slide. Correct answers here would be letters B and letters D. B and D both show a weak acid with its conjugate base. Here, letter B, we've got the weak acid hydrocyanic acid and its conjugate base, sodium cyanide. And in letter D, we've got the weak acid carbonic acid and its conjugate base. This would be potassium bicarbonate. Letter A is not a buffer because, while we do have an acid with its conjugate base, HBr, hydrobromic acid, is a strong acid. Letter C is not a buffer. While we do have a weak base, this is a strong base. So if we had, let's say, NH4Cl, then letter C would qualify as a buffer. But because we do not have, in this case, the conjugate acid to go with this weak base, it is not a buffer. All right, a few general guidelines on buffers. The best buffers have roughly equal concentrations of the conjugate pair. This means that here the weak acid and weak base, or the salt containing its conjugate, should have roughly equal concentrations. As mentioned, buffers can resist pH changes as long as neither component of the buffer has been completely consumed by any strong acid or base that has been added. And finally, of note is that a buffer generally loses its effectiveness when one component of the buffer pair is less than 10% of the other. So which of the following are effective buffers? Again, please pause the video and choose from these four which of them are effective buffers. Okay, answers here. Letter A would be considered to be an effective buffer system. We've got a weak acid, hydrofluoric acid, and its conjugate base with equal concentrations. Letter B is a buffer, but it would not consider to be an effective buffer system because we can see that these two concentrations are not within 10% of one another. We have a 1,000 to 1 ratio here in the concentrations. Letter C would be an effective buffer. We've got 1 molar ammonia, a weak base, and 1 molar ammonium chloride, its conjugate acid, with the same concentrations. And then once again, letter D would be considered to be a buffer, but it is not an effective buffer because their concentrations are not within 10% of one another. All right, let's practice calculating the pH of buffers. What is the pH of a buffer solution prepared from 0.30 molar formic acid, HCOOH, and 0.52 molar potassium formate, so KHCOO? So the formic acid would dissociate, forming H plus and the HCOO minus. We can see that the Ka of the formic acid is 1.8 times 10 to the negative fourth. So what we can do is set up an ice table. We've got 0.30 molar formic acid for its initial concentration, 0 for the H plus initial concentration, and 0.52 molar for the formate, the HCOO minus concentration. We will be moving in the forward direction since we don't have any H+, so minus X for the formic acid, plus X for both of the products, giving equilibrium concentrations of 0.30 minus X, X, and 0.52 plus X. Now, because this Ka is a lot less than 1, this means X is likely to be very small, and so what we can do here is use the small x approximation. So we can set up our Ka expression. Ka would be H plus times HCOO minus divided by HCOOH. We can plug in our values, X for H plus, 0.52 plus X for the HCOO minus, and 0.30 minus X for the HCOOH. Sorry about all the pauses today, and if you can hear the any background noise. I think they are weed whacking and leaf blowing outside my apartment. Anyways, I had left off here describing the dissociation reaction we set up, and so we can go ahead and set up our ice table. I was just mentioning how we can use the small x approximation, and then we can set up our Ka expression. Since we're using the small x approximation, the plus x and the minus x for both the formate and the formic acid can be ignored, making this fairly simple to solve here. And so we get x is equal to 1.8 times 10 to the negative fourth multiplied by 0.3 divided by 0.52. So basically this was multiplied from the left to the right, and then this was divided from the left to the right to isolate x. We get an x value of, sorry, I messed up my font here, 1.038 times 10 to the negative fourth. Then the pH is equal to the negative log of H plus, which here is just the negative log of x, giving us a pH of 3.984. And so this is one way we can calculate the pH of a buffer using an ice table. However, there is a little bit of a shortcut we can do here. So consider the equilibrium dissociation of a generic weak acid, HA forming H plus and A minus with some Ka. We'll call it 1 times 10 to the negative fourth. If we only had HA at the start, we would form both H plus and A minus according to the equilibrium given by the value of Ka. However, in a buffer solution, we are starting with some amount of A minus from the conjugate salt. The common ion effect means that HA will not dissociate very much to make more A minus, which means it's not making more H plus either. Essentially, what we can do here is consider the change, or the plus or minus x, to be very small. So if we consider that the change is very small, again, setting up an ice table, so whatever the initial concentration of HA is, 0 for the initial concentration of H plus, and whatever the initial concentration of A minus is, our changes are minus x, and plus x. Again, remembering that we're using small x approximation, which means these changes can be ignored. This means that the equilibrium concentration of HA is going to be approximately equal to its initial concentration, and same for the conjugate base equilibrium, approximately equal to the initial. What we can do then is we can take the initial concentration of HA and the initial concentration of A minus and plug that into our equilibrium constant expression. Then we're taking a few algebraic steps here. First, going from this step to this step right here, we're taking the negative log of both sides. So I'm taking the negative log of the left side, giving me negative log Ka, and I'm taking the negative log of the right side, giving me negative log of H plus times A minus divided by HA. Here we're making a substitution. The negative log of Ka is called the pKa. So this works pretty similar to what we learned about with pH, right? How the negative log of H plus is the pH. Same thing with Ka. The negative log of the Ka is referred to as the pKa. Then we're taking this log and we're splitting it into two pieces. First, we've got the negative log of H plus minus the negative log of A minus over HA. So basically, this part right here was separated into two separate logarithms. And then a final step is we're going to solve for the pH. So what's being done here? Notice here that negative log of H plus is defined as the pH. So this term right here, we're subbing in pH. And then we are isolating pH by taking this term and moving it via addition. And so this gives us pH is equal to pKa plus the log of A minus over HA. And this equation right here, a very important equation, this is referred to as the Henderson-Hasselbalch equation. So let's review how to use the HH, or the Henderson-Hasselbalch equation. So revisiting the problem we worked 3 slides ago, we're going to take our concentrations here and plug them in. So our initial weak acid concentration is 0.30. Our initial weak base concentration is 0.52. And our pKa can be found by taking the negative log of the Ka. So pKa here is the negative log of the Ka, 1.8 times 10 to the negative fourth, giving a pKa of 3.745. So this value can be plugged in right here. And then our logarithmic term, remember, it's the log of base over acid. So log of 0.52 divided by 0.30, and you solve and you get the pH being equal to 3.984. And note that this is the same value we got by solving for x in the earlier problem a couple slides ago using an ice table. So the Henderson-Hasselbalch equation works extremely well for calculating the pH of a buffer, since we're dealing with a weak acid and a weak base. So anytime you are asked to calculate the pH of a buffer, you should default to using the Henderson-Hasselbalch equation. It will save you a lot of time. Now, there are a couple assumptions here to mention with regard to the Henderson-Hasselbalch equation. We are assuming that we have a non-zero concentration of the weak acid and its conjugate base. We're also assuming the two concentrations are similar, roughly of the same magnitude. So basically, we're saying that the log of the acid, or the base over acid, should be between -1 and +1. This is basically just restating what we learned earlier about what makes an effective buffer, where the acid and the base should be within 10% of one another. So your effective buffer range is the pH should be within ±1 of the pKa of the weak acid. Now, these concentrations should be at least 100 times larger than Ka, because in our derivation of the HH equation, we use the small x approximation. And this equation will give inaccurate results with strong acids or strong bases. The pKa value needs to be between 4 and 10 for this approximation to work best. So really, it only works with weak acids and weak bases, which makes sense considering we're dealing with buffers here. All right, now there's a couple variations on the HH equation you may see. The one you're going to work with the majority of the time is this one here, the one we just established. pH equals pKa plus log of base over acid. But you may also see one for a weak base and its conjugate acid, BH plus, given Kb of the weak base. So this one is POH is equal to pKb plus log of BH plus over B. For a weak base B and its conjugate acid BH plus given Ka, we can say that pH equals pKa plus log of base over acid. And I do want to remind you that pH plus POH equals 14. Similarly, a very helpful thing to remember is that pKa plus pKb should also be equal to 14. I do want to note for any of my students, you will see this equation on the reference sheet. If you are given a buffer equation where either of these equations would be required, you would be given them. I'm not expecting you to memorize these. If you're not from my class, consult with your professor about what you're expected to memorize and what types of problems could show up versus what could be on a potential reference sheet you are given. All right, let's look at a little more practice with the Henderson-Hasselbalch equation. We're going to look at calculating pH of a buffer solution. This question states, what is the pH of a buffer containing 1 molar acetic acid and 0.5 molar sodium acetate, given that the Ka of acetic acid is 1.8 times 10 to the negative fifth? I would actually like you to try this one. So please go ahead and pause the video, see if you can come up with the correct answer here. All right, I'll walk you through. Oh, nope, sorry, never mind. I thought I had the work here. I do not. But here is the correct answer. The pH you should have gotten is somewhere around 4.44. So recall that pKa is the negative log of the Ka. So take the negative log of 1.8 times 10 to the negative fifth to find the pKa, and then it's just log of base over acid. So 0.50 goes here, and 1 molar, 1.00, goes right here, and you should get a pH of 4.44. All right. Now let's look at a problem where we are going to calculate the pH of a buffer after the addition of strong base. This problem states, what is the pH of a buffer containing 1 molar acetic acid and 0.5 molar sodium acetate after 35 milliliters of 0.80 molar NaOH is added to 2 liters of the buffer solution? Okay, so our problem-solving strategy here is first, we're going to consider the acid-base reaction between the added strong base, the sodium hydroxide, and the buffer's weak acid. It's helpful to do this in terms of moles to make things easier. Then you should use this number of moles with the total new combined volume Note that you have got that addition of the base to the buffer solution, so you need to find the combined volume to calculate the new resulting concentrations. If you still have non-zero concentrations of both buffer components, so the weak acid and the weak base, or I should say the weak acid and its conjugate, or the weak base and its conjugate, then you still have a buffer, and you can use the HH equation to find the pH. So let's start by considering the acid-base reaction here. We have got the weak acid, acetic acid, from our buffer, plus hydroxide from the strong base, so we're just going to consider the OH minus that's being added. So the OH minus reacts with the H plus from the acid to form water, and then we're also going to produce some acetate. We're going to consider this in terms of moles. So first, we've got 1 molar acetic acid and 2 liters of solution. This means that we've got 2 moles of acetic acid. Next, we'll consider the base. We've got 35 milliliters of 0.80 molar NaOH. So if you take that 0.80 concentration, multiply by the volume in liters, you get 0.028 moles of hydroxide. And finally, our conjugate base, we've got 0.50 molar of our sodium acetate, the conjugate base. Our volume is 2 liters. This gives 1 molar acetate. Now let's consider the reaction that's occurring here. So we're kind of doing an ice table here, but because we've got a strong base, this reaction is going to completion. So OH is the limiting reactant, and again, because it involves a strong base, this will go to completion. So all of that 0.0820 moles of the hydroxide gets used up. What this means then, since we've got a 1-to-1 ratio here from the coefficients, this will consume 0.028 moles of the acetic acid, and it will produce 0.028 moles of the conjugate base, the acetate. So we can see after the reaction occurs, all of the hydroxide gets used. We're left with 1.972 moles of the acetic acid, and now we have 1.0820 moles of the conjugate base, the acetate. Now that we've got these values in moles, we need to calculate the new concentrations. So first, consider the total combined volume. We had 2 liters of buffer plus the 0.035 liters of the base that was added, giving a total combined volume of 2.035 liters. We're going to take those mole values and divide by the new total volume to calculate the new concentrations. So dividing both of these, the 1.972 moles by the new volume and the 1.028 moles by the new volume, this gives us concentrations of 0.969 molar for the acetic acid and 0.505 molar for the acetate. Since we have non-zero concentrations of both the weak acid and the conjugate base, we still have a buffer, and we can use the Henderson-Hasselbalch equation to find the pH. So let's calculate the pKa. pKa is equal to the negative log of Ka, so this would be the negative log of 1.8 times 10 to the negative fifth, a pKa of 4.74 or 4.745. Now we can plug our values in, 4.745 for the pKa, 0.505 for the base component, and 0.969 molar for the acid component. This gives a pH of 4.462. And so this would be the final answer. The pH is now 4.462. I do also want to note that the original pH of the buffer was 4.444. So the pH went up slightly, but the buffer was successful in resisting the pH change, or at least a significant pH change. All right, now let's look at one more problem, calculating the pH of a buffer solution after the addition of strong acid. This one, we are again using 2 liters of the buffer solution with 1 molar acetic acid and 0.50 molar sodium acetate, but now we are adding 40 milliliters of 0.75 molar hydrochloric acid. Again, this problem solving strategy is pretty much the same. just a small difference in the first step. We are instead going to consider the acid-base reaction between the added strong acid and the buffer's weak base. We should again do this in terms of moles. Once we've got our mole values, we're going to divide by the new total combined volume to calculate the resulting concentrations. And then if we still have non-zero concentrations of both buffer components remaining, we still have a buffer, and we can use the Henderson-Hasselbalch equation. All right, so let's break these pieces down. We've got 1 molar acetic acid, 0.5 molar sodium acetate, and 2 liters of it would be our volume for both those components, and then 40 milliliters of the 0.75 molar strong acid. So let's write out our acid-base reaction. So this is going to be HCl, the strong acid, plus acetate. So again, just considering the base component here, the C2H3O2 minus the acetate. This forms some C2H3O2, so the H plus reacts with the base to reform some of that weak acid, and then Cl minus is what's left behind. Let's figure out how much of each we have. So first, the acid, 0.75 is our concentration, multiplied by the volume in liters, gives us 0.030 moles of the strong acid. Then we still have 1 mole of the weak base and 2 moles of the weak acid. Now we can write out our reaction. This, again, this is sort of works like an ice table, but because we have a strong acid, this reaction is going to completion, not to equilibrium. So the strong acid here is our limiting reactant, meaning all of the HCl is used. So we subtract 0.03 moles from the HCl. We should also subtract 0.03 moles from the base, since this is how much base is required to react with the HCl. And then we should add 0.03 moles to the weak acid over here. This is how much is produced. This gives us final amounts of 0 moles HCl, 0.970 moles of the acetate, and 2.030 moles of the acetic acid. Now let's find our new total volume. So 2 liters from the buffer, plus the 40 milliliters, or the 0.40 liters from the acid that was added, giving a total combined volume of 2.040 liters. I do want to mention a brief shortcut here. Since eventually we will be dividing these two concentrations, the volumes will cancel out since they are in the same volume, so we can actually omit this step and just use the number of moles directly. So you can do the mole step or the volume step to find the concentration if you prefer, since I did mention this in my problem-solving strategy, and I wanted to mention this because the values we learned in the Henderson-Hasselbalch equation are technically concentration values, but I do want to mention this shortcut since some of you have been wondering about this shortcut, because the weak acid and the weak base are in the same solution, they have the same volume, and so when you divide them, the volumes actually cancel out, which means that you can just plug the mole values in directly, and it's going to be the same mathematical ratio, and you should get the same answer. So we can set up our equation. We are working with the same weak acid, so our pKa value is still 4.74 or 4.745. Let's plug our values in. Plug in our pKa value of 4.745. We can plug in our mole values of 0.970 for the base, 2.030 moles for the acid. And when you work this out, you get a pH of 4.424. And again, note the comparison to the original pH of the buffer, which was 4.444. So a small drop in the pH. The solution got slightly more acidic, but this buffer was successful in resisting the pH change. Okay, now I would like you to try. I've got 3 buffer pH calculations for you. First, just calculate the pH of a buffer made with 0.75 molar HF and 0.95 molar KF. The Ka of hydrofluoric acid is 6.8 times 10 to the negative 4th. Then I've got 2 follow-up questions asking you to calculate the pH of the buffer after the addition of acid, and also asking you to calculate the pH of the buffer after the addition of some base. So please pause the video and take some time. This may take you a little bit longer, maybe 15, 20 minutes, maybe longer, maybe shorter, depending on how quick you are, and see if you can come up with the answers for these 3 questions. Okay, the answers are given here. Again, I'm not going to show the work here. The work is generally the same as the 3 problems I just went through. For letter A, you should get 3.270. For letter B, 3.267. And for letter C, 3.281. Okay, that concludes this topic, and that concludes this video. As always, if you have any questions, please reach out to me via email or leave a comment below, and I will do my best to answer your question as clearly as I can. But that's it for this one. I will see you in the next video, and I hope you have a great day.